Hello everybody, I know some of you have been waiting for this video. I'm not doing the whole paper now because I've been chilling out on half term. So I'm just going to focus on the multi-choice of 2017 paper 2. You will not believe how frustrating it has been trying to do this video. I started off doing 2017 paper 1 by mistake. Then I did paper 2 multi-choice like I'm doing now, but the video was recording in portrait instead of landscape. So, and there we are, third time lucky. Hopefully I can get through this paper. So what I want to say is thank you for those who are interacting with these videos. I think it's wonderful that so many of you are sending me email responses telling me where your strengths and weaknesses are. But for everybody who is doing that, there are some of you in my class who isn't, and I don't know where you're up to. And I don't know how we're finding it. I also know that there aren't as many views for these videos as there are people in the class. So some of you are going to really struggle come September because you haven't been interacting with these or engaging with these, and you'll be left behind by other people in the class if you're not careful. So you have got time to catch up, but you might end up having to use your summer holidays, which I have absolutely no sympathy for you. If you haven't been working hard on these, well, that's your fault. Other people have. All right. So I know some of you have got other reasons that you can't be doing the work, but I do need you to at least be watching these videos, at least taking part. Right, burette reading for this transparent liquid. Well, there's 24, there's 25. So the answer is going to be 24 point something. So it's not you or you. 24.1, 24.2, 24.3, because we read to the bottom of the meniscus. I've been ticking these on the previous videos. You've got to colour them in like that. Okay. Next. So now I'm just checking we are in portrait. Excellent. A volumetric flask. A volumetric flask looks like this. It's a particularly precise bit of equipment. It's used for measuring a single volume. In this case, we're measuring 250. We had some solute in there, which is a solid that you dissolve. You had a weighing container, so a weighing boat with solute, and then they've weighed the weighing boat after, so it might have some crumbs left in. So the difference between this and this is the amount of solute that's gone in. So that is 10.13 minus 4.48. I've just got my calculator on my computer here. 10.13 minus 4.48. 5.65 grams. So 5.65 grams of solute, which is the solid that's been dissolved, have gone in there. But to work out this value of 5.65, you've had to do two weighings. You did a weighing before and a weighing after. And each time you weigh, there is an uncertainty of 0.005. So in total, the uncertainty is 0.01, which is 2 times this. The percentage uncertainty is the absolute uncertainty, the 0.01, divided by the mass, or the mass that you weigh in this case, or the reading that you take. So it's 0.01 divided by 5.65 times 100. Because I've just done this video before, it's that answer. I'm just going to check it again on here. 0.01 divided by 5.65. Yep, it's that one, 0.18%. Right, next, infrared. Right, looking at this, first thing you do, cover up the fingerprint region because none of these peaks are important. All right, so you're looking at these sharp peaks around 3000, they are CH peaks. There is no alcohol, is there? So it's not an alcohol. What's the other peak that you've got? You've got this big peak at 15, 16, 17. That's 1700, large sharp peak. That's a C double bond though. So we're looking for an aldehyde or a ketone, butanone. It's you. Ethanol. No, there's no OH. Pentoene. No, there's no needle at 1600. Propanoic acid. That would look like that. They're easy then, aren't they? Infrared, if you've been doing the work that I've asked you to do. Bond angle around oxygen atom in ethanol. Right, oxygen atom in ethanol. Ethanol looks like this. Often it's drawn like that. But you need to know that the oxygens in organic molecules have got... When an oxygen is forming 2 bonds, it's got 2 lone pairs. This is rather like the oxygen atom in water. Anyway, what you can see here is the oxygen atom has got 2 lone pairs and 2 bonds. That means you've got 4 areas of electron density, which means you've got an angle of 109.5, but 2 of them are lone pairs, which knocks you down by a few degrees to 104.5. Just like in water, it's you. All right. What compound is a structural isomer? So a structural isomer is butene C4H8. So it's got to have the same formula but a different structure. Right, butane, no, that is C4H10, so it's not you. E-butene, that is a stereoisomer of Z-butene, so it's not you. Cyclobutane is C, well, CH2, 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 it's you. Because a structural isomer will either be a chain, a position, or a functional group isomer. Cycloalkanes are functional group isomers of alkenes. It's this. And why is it not D? Well, there's a butene with a methyl group. Well, that's going to be C5 something, so it's not that. The next one, which equation is a propagation step in the conversion of trichloromethane? Trichloromethane is this. There's methane with 3 chlorine, so CHCl3 into tetrachloromethane, which is CCl4. Right, it's a propagation step. Right, that's not a propagation step because it doesn't have any radicals. That's not a propagation step, that's a termination step because it's a radical plus a radical. These two look like propagation steps. Well, just looking at C, that's not like anything that we've seen before, so it's not you. D, that is the propagation step, it's this one. My battery power is now 5%, so I'm going to pause the video and go and plug this in. Alright, I'm back in the room. Thought that would be the icing on the cake, that battery running out after everything I've done already today. So, by the way, so if you wanted to do this, if we wanted to like properly work it out, CHCl3 plus, we do the radical there, Cl dot, we draw a Cl2 here, and an HCl up there, CHCl3, so the Cl, H and the Cl will go together, so you'll make CCl3 dots, then you have the CCl3 dot will react with the Cl2 to make CCl4 plus Cl dot. It's that one, you, anyway. But can you see how there's a quick way? That's not propagation, that's not propagation, that's weird, it's you. Right. Which compound has the fastest rate of reaction with potassium cyanide? Potassium cyanide is KCN. Potassium cyanide is basically CN- to form pentane nitrile. The words will throw you off here. This is a nucleophilic substitution reaction. Right, pentane nitrile is 1, 2, 3, 4, 5 with a CN on the end, with a C triple bond N on the end. And you make it by taking a 1, 2, 3, 4, 5 with a Br or an I or whatever. In other words, a haloalkane and a CN- comes in like that and does that. It's one of our nucleophilic substitution reactions. And what it's asking you is which of these 4 will have the fastest rate of reaction. And this is a part of the course that's it's a really, really simple idea. So which of these will react quickest? You've got 1 bromobutane, 1, 2... Oh, sorry, pentane nitrile. You include... Sorry, there is a mistake here. The pentane nitrile includes this carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4. So, my bad there. 1 bromobutane. 1, 2, 3, 4. 1 bromo. 1 chloro. 1 fluoro. Or 1 iodo. And the answer is 1 iodo because this carbon-iodine bond is the weakest of those 4. It's as simple as that. So 16 is D. There's a little section in your books that says that the speed of a nucleophilic substitution reaction with a haloalkane depends on the strength of the carbon-halogen bond. That's the strongest, then it's the chlorine, then it's the bromine, then it's the iodine. So in terms of speed, that'll be the fastest, that'll be the second fastest, that'll be the next fastest, and that'll be the slowest. Which alcohol can be oxidized? Can be oxidized by acidified potassium dichromate. primary alcohols, secondary alcohols, and tertiary alcohols. Well, tertiary cannot be, but cannot be dehydrated. Oh, right, so cannot be dehydrated. Dehydration using concentrated sulfuric acid. I'm going to have to draw these out. So, 2,3-dimethyl-butanol. 1, 2, 3, 4. 2,3-dimethyl-butanol. I'll put me 2-ol there. 2,3-dimethyl. CH3. CH3. What's all that about then? You are a tertiary alcohol. Therefore, you cannot be oxidized. Alright, so it's not you, because we're looking at can be oxidized but cannot be dehydrated. 2,2-dimethyl-propan-1-ol. 2,2-dimethyl. So again, I haven't gone through this paper before. I'm thinking on the spot. So if I make a horrible mistake, I'm sorry. Right, well, that one can be oxidized because it's a primary alcohol. And that one cannot be dehydrated. If I put the OH there and the H there, right, it can be oxidized. It's a primary alcohol, so you could oxidize that all the way to a carboxylic acid. But as to why it can't be dehydrated, to dehydrate this, when you dehydrate an alcohol, you make an alkene, and it requires you to take an OH and then a hydrogen off the neighbouring carbon, and this is the neighbouring carbon, this one, and that has no hydrogens attached. That one cannot be dehydrated. That is the answer, so 17 is B. I imagine a few of you struggled with that, so what I'm going to do, I'm going to show you C and D and tell you why it's not them. Propan-2-ol, 2-methyl-propan-2-ol. Alright, so 2-methyl-propan-2-ol. Okay, this one can be oxidized. If you have a look, it can be oxidized to a ketone. No, it cannot. That was so silly of me. I wish I hadn't have done that. No, that's a tertiary alcohol. 2-methyl-propan-2-ol. Wow, that was not very good teaching, was it? 2-methyl-propan-2-ol. That's a tertiary alcohol, so it's not you, because you cannot be oxidized. Pentan-3-ol. 1, 2, 3, 4, 5. Pentan-3-ol. OH. Right, it's a secondary alcohol, so it can be oxidized to a ketone. And it's got hydrogens on the neighbouring carbons here and here, so you could remove an H2O there and end up with a double bond here. Or you could remove this H2O here and end up with a double bond there. With this one, there is no hydrogen next to it. There's a carbon next to it. These hydrogens don't get involved. You can't put a double bond there. So that's that. Most people, when I've gone through these videos, the most common improvement that people say to their work is, I need to go through oxidation of alcohols, or I need to go look at oxidation and dehydration of alcohols. Yes, you do. Comes up a lot, and you notice it took me a little bit of time to explain, but I was certain it was B. Alright. How many structural isomers? Oh, I'm so bad at these. Have you ever seen me get one of these right in a lesson? How many structural isomers are there with a molecular formula C3H6BrCl? Structural isomers. Alright. Well, C3 makes it easy because it's 3 carbons in a line. And then you got a bromine and a chlorine. Right. Let's be systematic. You could have a bromine and a chlorine on the first one. I'm going to keep the chlorine where it is, and you can have a chlorine with a bromine there. Then you could have a chlorine here and a bromine there. Then you could have a chlorine on the middle and a bromine there. Then you could have a chlorine and a bromine both on the middle. Haven't drawn that one before. I started off systematically and now I'm sort of... Right, shuffle the bromine along. Yeah, now I'm bringing the chlorine across. Yeah, and then... I'd spend probably a bit more time in the exam, but I'm gonna go for B. Let's have a look at the mark scheme. 18. Yay! All right, but you know I can get them wrong in the exam. It's not good. It's not that they're hard. You just have to have a system, and I tend to. I'm surprised I got it right. Hey, so actually, cause for celebration. My little girl's about to come in, so I'm just gonna pause the video. No, I'm not. She's just doing my work, Jess. Okay, baby. Right. Which sample contains the most molecules? I'm gonna mute. So I'm gonna pause that because she's crying. Oh no, she's alright. Which sample contains the most molecules? Alright, so this is the number of particles in a mole of a substance. It's Avogadro's number. Pause. Okay, she's now crying. She wanted to do some painting with me. Anyway, so A, you just got to look which has got the most molecules. Well, this one you don't have to do anything with. You've got 21 times 10 to the 22. So what you're going to try and find out, is that going to win? 1 gram of oxygen. Right, well, 1 gram of oxygen, if I can work out how many moles of oxygen that is first, then I can work out how many molecules there are. Because there are 6 times 10 to the 22 in a mole. Right, I've got 1 gram. I'm going to divide it by oxygen, which is 32. Common mistake would be to put 16. Right, calculator. 1 divided by 32. 1 divided by 32. I'm trying to tap these keys hard so you can hear that I'm actually tapping them. So that's 0.03125 moles. If I times that by Avogadro's number, times, how do I do Avogadro's on this big, times 6. I don't know how to do times 10 to the 23 on this calculator. I'm struggling here because I haven't got a scientific. Scientific. Right. 0.03125 times 6. No. Can't do it. Right, I times that by this number times Avogadro's number. Next one, 65 milligrams. So I need to turn that into grams. So 65 divided by 1,000. 65 divided by 10 is 6.5. 65 divided by 100 is 0.65. 0.065. 0.065 divided by 2. 0.065 divided by 2 equals, so this is 0.00102 moles, which you then times by Avogadro's number, and this is 0.03 moles, which you then, because it tells you that you don't have to do anything with that many moles times Avogadro's number. So I've got 0.03 times Avogadro, 0.001. So out of these three, that one is winning. I just haven't got my calculator to work out if that's the biggest. So 19. Hey, that's the biggest number. Out of all of them, that's the biggest number. 23 times 10 to the 23. Oh yeah, times, well, it's that anyway. Okay, that would be a bit time consuming in an exam maybe. Which compound forms a molecular ion with a different precise molecular mass? Right, a molecular ion is something that you put through a mass spectrometer and it's M divided by Z. All of these molecules, you can put them through a mass spectrometer. So butanone, C4H, 1, 2, 3, 4, 5, 6, 7, 8, C4H8O. You put that through a mass spectrometer, it gets ionized, it blasts through and it comes up with a peak. Beep. The heaviest peak is known as the molecular ion, sometimes known as the mass ion or the molecular ion, and that would come through weighing whatever butanone weighs. Alright, you'd also see some fragments, but whatever. So butanone, you'd see a molecular ion, this furthest right peak. So the precise molecular mass, molecules will only have the same precise molecular mass if they've got precisely the same formula. So C4H8O. Cyclobutanol would look like this. There's an ol. So this is an exercise, and do you know what the formula of these is? So that's C4H 1 2 3 4 5 6 1 2 3 4 5 6 7 H7OH, which is C4H8O. They would have exactly the same precise molecular mass. Dimethyl propane. Dimethyl propane. Well, hang on a minute. That's 3 carbons plus 2 other carbons. So I know straight away that's going to be C5 something, which means it won't be precisely the same as these two. Whereas this is methyl prop, 4 carbons. Well, it's got to be C, because that's got 5 carbons and the other ones of them have got 4. So I don't need to go any further. The answer to that is C. Alright, cool. Do you notice how I was going down one route of working out the formulas, and then I just suddenly thought, well, I'm looking for C4H8O. Well, I know that this has got 5 carbons, so you can change your plan halfway through. I could have worked this out, dimethyl propane, 1, 2, CH3, CH3, oh, that is C5H blah, 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 and then I could have done this one, but you should be noticing by C that that's different. Anyway, hydrogen can be produced by this reaction. Remember, hydrogen is H2. Carbon monoxide plus water makes carbon dioxide plus hydrogen. In an experiment, 4.2 moles of carbon dioxide, 4.2 moles, so I don't need to do anything with grams or anything like that, were mixed with 2 moles of steam. 2 moles of steam. Alright, so it's one of these equilibrium ones, so there's 0 of that and 0 of that. That's the initial. When the reaction reached equilibrium, so you work out equilibrium moles now. When the reaction reached equilibrium, 1.6 moles of hydrogen have been formed. So this has gone to 1.6. So this has gone up by plus 1.6. For every mole of this form, there's a mole of this form. So this will go up by plus 1.6 as well to 1.6. The product will go down. This is 1 to 1 to 1. So this will go by minus 1.6 to 0.4. This will go minus 1.6, 4.2, 3.2 to 2.6. What is the value of the equilibrium constant for this reaction? Equilibrium constant equals the concentration of that divided by the concentration of that divided by the times the you know what I'm doing. Alright. Now, normally what you'd have to do here, so these are just moles. So in here, these are concentrations, so you'd have to do moles divided by volume. But in this case, because these concentrations all cancel out, you are allowed to just use the values for the moles. So normally what I'm saying is you would do 1.6 divided by volume times 1.6 divided by volume divided by 2.6 divided by the volume, overall volume. Alright, but all of these volumes cancel out, so you don't need to do that in this case. Anyway, so it's 1.6 squared divided by that, divided by that. I'm just going to look on the answers here because I can't bother getting my calculator out. C. 1.54. No. D. 2.46. I'm going to try and do it on the calculator now, make sure I do get that value. So 1.6 times 1.6. 1.6 times 1.6 equals 2.56 on the top, divided by 2.6 times 2, which is 5.2, divided by 5.2. What have I done there? Me not like this. What is the value of the equilibrium constant? That did not give me the right answer. Because that's not 2. That's 0.4. Silly man. Right, let's do that again. 1.6 times 1.6 equals 2.56. And then 2.6 times 0.4. 1.04. So 2.56 divided by 1.04. 2.46. Sorry. But I wouldn't have got, in the exam, none of those were the answer that I got. So anyway, I'd have known I'd have got it wrong. Right, a sample of 2 mole per decimeter cubed acid has a volume of 100 centimeters cubed. So we've got some acid, it's 100 centimeters cubed, there's a beaker there, 100 centimeters cubed, and it's 2 molar, 2 moles per decimeter cubed. I've got a concentration and a volume. What volume of water in centimeters cubed should be added to this acid to dilute the sample to a concentration of 1.5? Right. So, firstly, So, what have I got? I've got 2 moles per decimeter cubed times 100 divided by 1000. So, in the first sample here, I've got 200 divided by 1000, 0.2 moles of acid. That's how many moles of acid you've got in this beaker. Now, if you're going to pour a load of water on top of that beaker, you're not going to change the moles of acid. So the number of moles of acid is going to be 0.2 in the second situation. You're still going to have 0.2 moles of acid, and you're aiming for a new concentration of 1.5 moles per decimeter cubed. So all you need to do is work out the new volume. So if moles equals C times V divided by 1000, if we take the moles and we times it by 1000, so we take the 1000 up here and then divide it by C, that'll give us the new volume. So I'm going to do 0.2 times 1000 divided by 1.5. 0.2 times 1000 equals divided by 1.5. 133.3 recurring. 133.3 recurring centimeters cubed is now the total volume of this solution, which means that I needed to add 33.3. So even though this looks really, really hard, pause that one, go back and see what I did. It's just work out how many moles of acid you add and then plug that into the moles equals CV over 1000 with your new target concentration. I hated them when I was in school. I really did, like as in when I was a student, because I thought they were really hard until I realised that they weren't. Alright, I'm running out of space on my memory card. Right, 2 sealed flasks with the same volume are left side by side. 2 sealed flasks with the same volume, 2 sealed flasks, there they are, with the same volume, same V, are left side by side. I'm already worried I'm going to get this wrong. Flask A contains this many moles of methane, 4 times 10 to the minus 3 moles of this gas, methane. And this contains 340 milligrams of a gas, but I don't know what the gas it is, so I don't know how many moles there are. Both gases are at the same temperature and pressure. So, so what we're saying is the volume in each of these is the same. Hang on then. What's this going to be? I think it's this. Right, we know that PV equals nRT. So we know that the volume equals nRT divided by P. And we know that the volume in flask 1 equals the volume in flask 2. Is that right? Yeah. The volume in flask 1 equals the number of moles in flask 1 times this, which are the same. Alright, and the volume in flask 2 equals N2 divided by P. So because V volume in 1 equals the volume in 2, that means that the nRT divided by P in 1 equals the nRT divided by P in the other. I'm getting somewhere here. I don't know where, but I'm getting somewhere. The T and the P and the R are the same in both flasks. So the R and the T and the P are the same in both flasks. Okay, I'm thinking this through as I go. So they're all going to cancel out. So what is important here is the number of moles of gas in one must be the same number of moles in the other. So I need to work out which of these compounds will give me 4 times 10 to the minus 3 moles. Right, so, my kids are being noisy, it's doing me head in. I'm thinking, shh, Children, be quiet. Right. This is... I need to work out moles. Right. I'm going to just pause this video. They're going to really annoy me now. Okay. That was very, very stressful. I've got a mass, and I know... So basically, I need to make this... I need this to be 4 times 10 to the minus 3 moles. Mass divided by the MR equals moles. So 340 milligrams, 0.34 grams, 0.34 grams divided by a number equals 4 times 10 to the minus 3. 0.34 divided by x equals 4 times 10 to the minus 3. So 0.34 divided by 4 times 10 to the minus 3 will equal x. Right, I just rearranged that there. I'm going to clear this on my calculator. 0.34 divided by 4 times 10 to the minus 3, 0.004, 85. So I'm looking for something with an MR of 85. 12, 13, 14, 35 plus... it might be you, hang on. What's chlorine? 30, where's my period table? 35.5. 35.5 times 2 is 71. 81, 82, 83, 84, 85. 85. Might be it. Yeah, 23 a day. That's got an MR of 85. So let me go through this again. This has got an MR of 85. So if you've got 340 milligrams of it, that means you've got 0.34 grams of it, which means that you've got 4 times 10 to the minus 3 moles of it. 4 times 10 to the 3 moles of gas, 4 times 10 to the 3 moles of gas. I didn't need to do all of this really if I'd have thought very clearly at the start that it doesn't matter what gas is in there. If you've got the same number of moles of any gas will occupy the same volume. That's what all of this bit in the middle means. I hope if you pause that and think about it and go through it again, all you've seen me there is sort of get to it in my own way. But I got there. Analysis of a sample with a chemical formula showed that it contained 0.195 moles of carbon. What mass of nitrogen was present in the sample? Okay. A sample of a chemical had that many moles of carbon.